step into an exploration of the progression of cosmic measurements, demonstrating how light from remote sources shifts in wavelength as the universe expands, an ongoing process that began billions of years ago. This observable expansion has gradually changed the positions of celestial bodies, leaving behind evidence embedded in the altered shades of ancient light. Capturing these shifts is not merely an act of gathering data, it is the unfolding of a story written across time itself. The slow transformation of light unveils how matter, once densely packed, has spread out to form the intricate structure shaping everything that exists. Simultaneously, our own presence becomes a fragment of this vast chronicle, a small yet inquisitive element in a timeline that stretches far beyond human experience. Today, we will examine how the steady yet unstoppable expansion of the cosmos has influenced the distribution of all surrounding material and structures. Picture yourself beneath a starry night sky, realizing that the luminous dots above are not motionless. They are part of an ever-evolving tale. Our journey will follow how space extends over time, with distant galaxies appearing to drift apart. This movement is not simply celestial objects wandering aimlessly, it is the very fabric of space stretching. Scientists measure this through a phenomenon known as redshift, where light elongates into longer, redder wavelengths as it traverses the ever-expanding cosmos. Our exploration begins with a discovery made decades ago when astronomers observed that light arriving from distant galaxies appears elongated and shifted toward red tones. Imagine witnessing a familiar pattern gradually change in color, revealing that the separation between us and those remote points is increasing. The earliest observations resembled inflating a balloon, each marked point moving farther apart as the surface expands. This provided the first indication that the universe is dynamic rather than static. However, this is not merely about galaxies drifting away. The ongoing expansion has also reshaped the very framework of the universe itself. In its infancy, the cosmos was dense and brimming with the essential ingredients for star formation. Under such conditions, vast clouds of gas rapidly condensed, giving rise to brilliant, energetic stars. Yet, as space stretched over time, this material became more dispersed. This progressive thinning of matter reduced the ideal conditions for star formation, leading to a gradual decline in the birth rate of new stars, though we will delve deeper into that later. The diminishing concentration of matter plays a pivotal role in the cosmic story. As galaxies separate and their building blocks spread out, the energy required for new stars to emerge becomes less accessible. Over time, the universe transitions from a phase of intense activity to one where aging stars dominate, and the birth of new stellar bodies becomes increasingly uncommon. This transformation not only alters the appearance of galaxies, but may also significantly affect planetary systems, shaping the foundation of a quieter, more solitary cosmic future. Abundant evidence supports this unfolding narrative. Astronomers employ various methods to piece together the puzzle of cosmic expansion, measuring the redshift of countless galaxies and utilizing standard candles, astronomical objects with known brightness, to confirm that the farther an object is, the faster it moves away. Observations over the past century even suggest that this expansion is not merely continuing but accelerating, adding a layer of mystery to our understanding. The realization that space itself is not only stretching, but doing so at an increasing rate brings us closer to unraveling the long-term destiny of cosmic structures. The extension of space affects everything, including the mechanisms that give rise to stars and eventually lead to their demise. In many spiral galaxies, enormous clouds of gas and dust serve as the cradle for stellar birth. These nebulae, functioning as cosmic nurseries, contain the essential materials required for new stars to ignite. Due to gravitational forces, denser regions within these clouds begin to collapse, heating up as they compress. Once the temperature reaches the necessary threshold, nuclear fusion ignites at the core, marking the emergence of a new star, a process that repeatedly unfolds within the spiral arms where fresh material remains plentiful. By contrast, elliptical galaxies present a different scenario. Over time, the processes responsible for forming stars in these galaxies have consumed most of the available gas, leaving behind a population of aging stars, remnants of an era when conditions were more conducive to new celestial births. This phenomenon is further amplified by the ongoing expansion of space-time as limited interstellar gas remains to sustain new star formation. As a result, these galaxies take on a dimmer appearance, their stellar populations aging in quiet isolation. A star's existence is dictated by the gradual depletion of its nuclear fuel. In its prime, nuclear fusion sustains its brilliance, but as fuel reserves diminish, whether over millions or billions of years, the star's energy output weakens. Depending on its mass, a star may conclude its life in a violent explosion or simply cool and fade away. Regardless of its final stage, this process contributes to the overall decline of star formation within galaxies. As a galaxy's stellar population ages, profound transformations occur. In regions where gas remains abundant, star formation persists, replenishing the galaxy with youthful, radiant stars. However, when gas supplies dwindle, as seen in elliptical galaxies, the birth rate of new stars dramatically decreases. Over time, this leads to a galaxy dominated by aging, dim stars, with the processes that once fueled stellar creation coming to a near halt, ultimately contributing to the formation of a cosmic void. The cycle of stellar birth and death follows the rhythm of cosmic time, leading the universe into an era of gradual dimming. Even the most resilient stars, red dwarfs, known for their extraordinary longevity, will eventually exhaust their nuclear fuel. As these long-lived stars fade, the collective glow of countless galaxies diminishes, transforming a once brilliant cosmic landscape into an increasingly subdued expanse. The slow fading of stellar populations hints at a future where the processes that drive star formation come to an end. One by one, stars burn out, and galaxies transition into collections of ancient remnants. The silent presence of white dwarfs, the dense cores left behind after nuclear reactions cease, stands in stark contrast to the fiery beginnings of their progenitor stars. Alongside them exist neutron stars, the compact remains of stars that survived explosive supernovae, and the enigmatic black holes, whose immense gravitational pull defies conventional understanding. These celestial remnants underscore the inevitability of this long cosmic twilight. As stellar light fades, the universe undergoes an even more profound transformation. With fewer active stars radiating heat and energy, the cosmos gradually cools, a scenario referred to as the Big Freeze, or heat death. Over unimaginably vast timescales, the embers of dying stars will cool to near absolute zero. Even the supermassive black holes at the centers of galaxies will not be immune to this fate, eventually evaporating due to Hawking radiation over timescales estimated at 10 years. In contrast to this slow decline, another possible scenario envisions a much more violent end, the Big Rip. If dark energy, the force driving cosmic expansion, continues to intensify, it may ultimately overcome even the strongest forces binding matter together. Galaxies would first unravel, followed by the disintegration of stars and planets, and eventually the destruction of matter at the atomic level. If this prediction holds, the Big Rip could occur in approximately 10 2 years, tearing apart the very fabric of the universe. Alternatively, some theories propose that the expansion of the cosmos could reverse, leading to a big crunch. If gravity eventually overcomes dark energy, the universe may contract, pulling all matter back into an incredibly dense point. Under such extreme conditions, physics as we know it would cease to apply, potentially paving the way for a new beginning, another Big Bang. While these cosmic fates unfold over timescales beyond human comprehension, the challenges we face on Earth are immediate and pressing. The grand narrative of the universe, filled with gradual decline and distant catastrophes, contrasts sharply with the rapid changes shaping our planet today. Climate change, pandemics, and technological upheavals present urgent concerns requiring both immediate action and long-term foresight. The same scientific curiosity that allows us to study the fate of the universe also guides our efforts to protect our world. As we navigate an ever-evolving landscape of discovery and uncertainty, the spirit of exploration remains essential, not only for understanding the cosmos, but for securing the future of life on Earth.